So in this video, we'll be relating the cell potential of an electrochemical reaction with that reaction's equilibrium constant and its Gibbs free energy value. Then I'll be discussing the Nernst equation, which is how we deal with reactions that take place at non-standard conditions. Just to get right into it, we can calculate the free energy reaction by taking the negative cell potential, multiplying it by the Faraday constant, and the number of moles of electrons involved in the balanced net ionic equation, the ones that you usually get to cancel out. So if I take the water electrolysis from our previous video, the water electrolysis has an E standard value of negative 2.36 volts. Right? So this is our water turning into oxygen and hydrogen gas. Now, for this process, N is the number of moles of electrons, right? So the number of moles of electrons is 4 because our two reactions, one of them involved 4 moles of electrons, the other involved 2 moles of electrons. So when we balance them to cancel out, they cancel out at 4. Right? So those are the two numbers we're going to need here. So all we have to do to find delta G is going to be equal to negative 4 times 96,500 times negative 2.36, which gives us a value of negative 900, sorry, not negative, positive 911 kilojoules to sig figs. Right, it's 910,960 joules, which to 3 sig figs is 911 kilojoules. Right? And this shouldn't surprise us because it's an electrolysis problem, which means that it's non-spontaneous. So delta G should be positive. Right? Now, to go between cell potential and the equilibrium constant, we're going to plug it into this equation right here. If you actually do care, there is a version of this equation that uses base 10 log instead of natural log, but I don't think it matters really to us that much to get examples in with it. Right, so to find the equilibrium constant for this, first thing we're going to do is we're going to rearrange and solve for K. Right, so we're going to have E standard and F over RT is ln of KEQ. Right, we'll just E both sides of this. So KEQ is E standard and F over RT. Now, keep in mind, which R do you think we should be using here? Right, we should be using energy R when we go and do this. Right, so plug everything in, and we're going to get negative 2.36 times 4 times 96,500 over 8.314 times 298, parentheses around the whole thing, e to that. And when we finally plug all this in, we get an equilibrium constant of 2.08 times 10 to the negative 160th. Yes, you heard that right. Negative 160th. The thing about electrochemical equations is that their equilibrium constants tend to be either really, really small or gigantic. So it's not out of the realm of possibility for you to have spontaneous reactions give you a K value somewhere in the range of 10 to the 80th. Right, so don't freak out when you see that. These numbers are correct. Right, so that's how we can relate electric cell potential to free energy and equilibrium. So just to give us a little bit of a review and kind of connect all these things together, because way back when we talked about Gibbs free energy and equilibrium constant, I gave you the equation that's in the upper right-hand side of the triangle. Right, so those three equations allow you to convert very easily between any of the three values. We just also need to keep in mind conceptually that a spontaneous reaction has a negative delta G, positive E, and K greater than 1. Non-spontaneous reactions have a positive delta G, a negative cell potential, and a K value that's less than 1, while at equilibrium, delta G and the cell potential are both 0, which is why when a battery reaches equilibrium, by the way, it dies because E is equal to 0, and a K value of 1. Right, so that's just connecting all those concepts together in one nice, neat little package. Now, one thing that we do have to talk about a little bit is what happens if we deviate from standard conditions, right? All the math we've done to this point has involved occurring at 1 molar solutions, 1 atmosphere pressure, and temperature of 25 degrees Celsius. If we change that, we have to account for that. Now, we could do it using something involving equilibrium and cell potential if we only had a value that we could use when we weren't sure if the reaction was actually at equilibrium or not. Oh wait, that's right, we do. It's called Q. Well, I guess we're in business then. Right, so the equation that I have here is what's called the Nernst equation. Now, this will give you the cell potential of any reaction based on its standard cell potential under standard conditions and the value of Q using a form of the equilibrium equation that we had in the previous couple of slides. One thing that I should probably point out to you is that this equation is not required to solve any problem on the AP Chem exam. So because of that, it's not included on the equation sheet. You can perfectly well answer any conceptual question regarding non-standard conditions just by treating it like a Le Chatelier's principle problem. You changed from equilibrium. How does that change affect the reaction? Which way is it going to shift? And what will that do to the cell potential? Right? If the forward reaction cell potential is increased, E goes up. If the reverse reaction cell potential is increased, E goes down. With that said, if you decide to use the Nernst equation as part of your justification and you use it properly, you will still receive credit for it. Right? And a fairly cool application of the Nernst equation is something called a concentration cell. Right, so in this cell, what we have is we have 2 copper half reactions. 1/2 reaction is copper 2 plus, picking up a couple of electrons to become copper metal, and the other is going to be copper metal losing 2 electrons to become copper 2 plus. Now, looking at this, you would expect this reaction to produce no voltage because the forward reaction and the reverse reaction are exactly the same thing, right? So their E should cancel out because one E is plus 0.34 volts, the other E is minus 0.34 volts. Those add up to 0. But the thing that we have to notice here is that the concentrations are very different. One of our solutions is at 1 molar. The other solution is at 100th molar. Now, because these concentrations are so different, our basic knowledge of equilibrium should indicate to us that the copper ion concentrations in these 2 solutions will eventually equal out. Right? So what that means is that the 0.01 molar solution has to become more concentrated, and the 1 molar solution has to become more dilute. Since this shift still has to occur, we're not at equilibrium, so K isn't equal to 1 yet. Right? Since K isn't equal to 1, ln of K isn't equal to 0, so that whole negative RT over NF ln of Q doesn't actually cancel out. There will be a non-zero value here. We can plug in the numbers and actually determine that we're going to get a very small voltage to this. For this particular cell, I would estimate the voltage to be somewhere in the range of a few hundredths of a volt. So it's not very much, but it is still a non-zero amount, and it can actually be used to power cells that require very minimal voltage, right? So not only is this the last slide of the video, but it's also the last slide of the AP Chemistry curriculum. So go get ready for the AP exam, and good luck.